Every GPT model, with billions of parameters, is ultimately built from the absolute simplest mathematical object imaginable, a single number. So let's dive right into this explainer, strip away the magic, and look at the foundational matrix mathematics behind artificial intelligence.
It honestly sounds completely unbelievable, right? We constantly hear about these massive models with hundreds of billions of parameters doing things that feel, well, almost human. But at the end of the day, every single GPT model is built entirely from just a solitary, lonely number. In math and physics, we call this a scalar. Literally everything an AI thinks or predicts traces straight back to this one simple concept.
Section 1. The simplest mathematical object. Before we can understand the complex linear algebra powering AI, we have to start with this basic atomic unit.
By mathematical definition, a scalar is simply a single numerical value. It possesses a specific magnitude, but, and this is absolutely crucial, it completely lacks any physical direction. It just tells you how much or how big something is. Nothing more, nothing less.
It could be a basic, everyday positive integer, like the number 5.
Or it could be a simple negative integer, like -3.
It doesn't even have to be a clean round number. It could be a famous infinite mathematical constant, like pi, representing roughly 3.14.
Or it could be a ridiculously tiny decimal, like 0.0001. No matter how massive, microscopic, or messy the number is, as long as it's just one single value standing totally alone, then yep, it's a scalar.
Moving to Section 2, Real-World Scalar Quantities. You might be thinking this sounds like a pretty dry math lesson, but you actually interact with these things every single day without even realizing it.
When you wake up, check your weather app, and see a temperature of 32 degrees Celsius, that is simply one number, a scalar. It tells you how hot it is outside, but that temperature doesn't point north or south, right? It just is.
The exact same concept applies to measuring weight. Step on a scale and see 70 kilograms. That magnitude is a scalar.
Or think about someone's age, like being 22 years old. Time keeps moving, for sure, but your age as a specific measurement is just a single scalar value.
Even something like a salary of 1 million rupees or glancing down at your dashboard to measure a speed of 60 kilometers per hour, each of these is just one numerical value representing a specific amount.
So, the big takeaway here is this specific progression. We're taking one number, mapping it to one quantity in the real world, explicitly with zero direction. This is entirely unlike complex physics concepts like velocity or force, which actually have to point somewhere. A scalar just sits there, perfectly holding its value.
All right, Section 3, Scalars and Computer Programming. Let's see how this builds into the digital world, which is basically the waiting room for artificial intelligence.
When you're setting up a machine learning script in Python, every single variable you define is fundamentally a scalar. You might set a learning rate of 0.001, a bias of -1.2, or even a generation temperature of 0.8. In the computer's memory, these are just solitary numbers. They're literally the dials and knobs engineers tweak to tune a system.
Section 4. Math behind neural networks. So, how do we jump from a simple Python variable to a system that actually understands human language?
Well, a neural network contains millions, or in the case of modern large language models, billions of these exact scalar values. If you were to crack open a neural network and look inside, you wouldn't find thoughts or concepts. You'd find this: a weight of 0.53, a bias of -1.8, a loss metric of 2.41. These scalars make up the basic atoms that process complex AI decisions. They are the literal parameters you hear about when companies announce a massive new 70 billion parameter model.
Our sources really emphasize this hidden language of AI. And yes, while those sources discuss incredibly complex mechanisms like huge matrix multiplications and activation functions, it is vital to remember that absolutely everything in those systems begins as a scalar. Before a matrix can even be multiplied, it has to be filled with these individual numbers.
Let's look at Section 5, how GPT uses scalars. We're going to dive into how a massive model practically uses these numbers when you type in a prompt.
When you feed a word into GPT, it doesn't read the letters. It translates that word, let's say the word apple, into a token. In GPT, one single word token might become an embedding size of 768, and every single entry in that huge list is just an individual scalar. So 0.12 might represent a tiny sliver of the concept of fruit, -0.81 might map to its color, 1.22 could represent crunchiness. The AI's entire comprehension of the word apple is quite literally just a long column of 768 distinct scalars. Which brings us to Section 6, From Scalars to Vectors. But here's the catch, and it's a huge one. A single scalar isn't nearly enough to represent a complex, abstract concept on its own.
The number 0.12 by itself means absolutely nothing to GPT. To create actual intelligence, we have to scale up from an isolated atom to a complex molecule. We do that by grouping these single directionless numbers into a highly structured collection. So we go from a lone 0.12 to a massive, ordered list that paints a complete mathematical picture. Which leaves us with a pretty profound question to chew on as we wrap up this explainer. If an AI is basically just a giant ocean of disconnected individual scalars, how do we mathematically organize billions of them so that a neural network can actually process information, recognize patterns, and effectively think?
Well, that level of organization requires stepping up to the next core concept of linear algebra, the vector. It's the mathematical bridge between a simple number and artificial intelligence, and it is exactly what we're going to explore in our next explainer. So keep this simple scalar in your mind, because it's about to multiply into something truly extraordinary.